Now this video explained the over reinforced section and design of singly reinforced rectangular sections. Now over reinforced sections, we talk about the moment capacity of under reinforced. We talk about balance section in previous video. Now we just talk about over reinforced sections, and then we move on to the design of singly reinforced rectangular sections. Now over reinforced section, just as of the balance sections, an over reinforced section is not permanent in the beam, but it is unavoidable in column. So like balance sections is not permitted because it's non-ductile behavior, and the over reinforced section is not permitted because it's the non-ductile behavior. Just under reinforced section is permitted. Now let's move on to the design of singly reinforced rectangular sections. Now design moment capacity 5 mu, and then capacity factor 5 is 0.85. so that is given in Australian standard on page number 36, AS3600 2018. We have bending, section B, we have bending without axial compression and tensions. So in that case we can see that the capacity factor 5 is 0.85, that is we taken. Now the design reinforcement for bending strength everywhere along the beam is, we need to satisfy this condition that the capacity of the beam is greater than the design moment. So design moment is generally obtained from the bending moment diagram. This is a typical case for the simply supported beam. Now to ensure the adequate ductility, the neutral axis depth Ku is limited to 0.36. Recalling that we know that Ku is equal to dn on d, and we checked in the previous video and substituting into dn equations. Now previously we look at this on dn equations. And so to you in the previous video we obtained, in the case of MUO under reinforced rectangular section, we obtained this dn equations. I use this dn equation again here, write it down here. We divided dn on the left side by d, and we divided by dn on both side d. So in that case dn on d is Ku, that is the Ku is a ratio of depth of the neutral axis to the d, is 1 over alpha 2 Fsy, and this is the maximum reinforcement, is the ratio of AST on B on D. Please note this B on D is nothing but if I take the reinforcement, now this is a D and this one is a B, and if I have a neutral axis, that is a Dn. So this is a typical and this is the area of AST. This is a typical notation for these symbols, and we substitute Ku equal to 0.36, that's the requirement. So 0.36 is equal to 1 over alpha 2 Fsy AST, and we substitute AST By, so this is the maximum reinforcement required. So maximum reinforcement required is 0.36 times alpha 2 gamma times Fc dash over Fsy. Now to avoid the possible fracture of tensile steel when the crack first develop in the beam, a minimum proportion of the reinforcement, we need to know P minimum as well, like we know P maximums, and what is the minimum reinforcement ratio required to ensure that MUO is greater than 1.5 FCT dash Fz. Now Z is nothing but is the section modulus of the uncracked sections, which is moment of inertia over centroid distance y, using the distance y, and the y distance is nothing but this distance from the neutral axis to the bottom fiber, centroid axis to the extreme fiber in tensions. Note that in the negative bending, tension will be at the top of the sections. So this is just a beam section, and this is FCT dash F. Now for rectangular sections like that shown above, this minimum reinforcement required reduces to, so we have minimum reinforcement of 0.2 capital D. This capital D is nothing but this is the capital D, and small over small d. Small d is nothing but this is small d square FCT dash over Fsy. Hence the amount of tensile steel P is AST on B D actually provided every sections along the beam must be such that we have this reinforcement should have a range between maximum reinforcement and the minimum reinforcement. The equation is given. Now note that In heavily reinforced sections, it may be necessary to place the tensile steel in two layers separated by space bar. So sometimes we need to put the two layer of reinforcement, and we have a space bar here as shown in figure. Ensure that clear spacing S, which is this one, should be greater than the maximum aggregate size. So you should have the spacing that allow to settle this aggregate. Thank you. And so this is a quick video on the design of singly reinforced rectangular sections. Thank you.